Please tell me that you tried these example problems after I told you to at least do them again. No one knows if you have them wrong. They're not going to be graded. So what's it going to hurt to take a few minutes and just attempt the problems to see if you can come up with the right answers? You might surprise yourself, actually, if you do decide to do these types of things. So this question, what products are formed? Notice it says products with an S, because two clear products are formed in these reactions because the ether splits in half. So what would be formed if the following ethers react with HI? Okay, so let's tackle the very first one. So what I have is a with an oxygen and then a boink boink. The issue is that we have a double bond there. We haven't really seen a double bond in the examples that I gave you, but it doesn't matter because the mechanism stays the same. And we're going to react it with HI. So there we go. Okay, well, the hydrogen protonates the O. The O will decide to leave. We just got to figure out which side the oxygen will break on. That's the purpose of these reactions. So no mechanisms, no curvy arrows, just predict the products, folks. That's all that we're after. So, will the oxygen cleave to the left, or will oxygen cleave to the right? That's the question. It's always the question with ethers. If it cleaves to the left, we will end up with a carbocation that's here. That carbocation, well, this is a carbon that's on another carbon that's right there. And if it cleaves on the right-hand side, the carbocation will end up here. And this is a carbon, and there's another carbon that's there. So you're looking at these and you're thinking, okay, well, this is attached to only one other carbon, so this is primary, and this is attached to only one other carbon, so maybe this is primary as well. You're looking at this as a tie, and you're going to say, well, it's the one that's least sterically hindered. No. There's a difference between these two. Folks, the difference is that this double bond is on a carbon, and right next door is a positive charge. This is delocalization that can take place. That's why they put that double bond in there. I mean, you knew they had to do it for a reason. They either had to trick you, or it actually played a part in the decision. And here, it's the latter. So even though this is a primary carbon that will be left behind, this primary carbon is stabilized because of the delocalization that can take place. The double bond can actually move toward a positive charge. That was the whole delocalization lecture that we did in Chemistry 251. So because of that, I'm going to redraw the reagent. You know that's how I work. You knew it was coming, so there you go. And I now know that when this oxygen protonates, it will probably prefer to cleave the bond right here. Bing, there it goes. And that oxygen will now take the hydrogen away and form the alcohol. What we have left over here on this side is a carbocation. That carbocation, whether it fully forms or not, it doesn't really matter at this point. That is what's going to accept the iodine. So this is the halogenated piece. So we have this carbon, double bond carbon with an I, and then we have this OH group that's on a carbon-carbon. Those are the two products from this split of the ether that's due to the acid addition. Now let's take a look at B. B, they give me a ring, and this ring here at the bottom has an O group on it. That's my ether. I'm going to react this with HI. I want to know what kind of products get formed. Okay, well, I know I'm going to start with a ring. I know that's for sure, and there's the oxygen on it. So the hydrogen protonates the O. The O makes a decision on what to do. And the O looks at the left and looks at the right in this case. And guess what, folks? It's the same. There's no difference between these two. Who cares what you do here? You're just going to erase one of the bonds. Boom, there it goes. Because that oxygen now has a hydrogen that it needs to make happy. And then on the other side, well, this is going to be the group that's going to get the nucleophile, and that's going to be the iodine. So the ring will open up. And on one end, we have an OH group, and on the other end, we have an iodine. Now, if you want to leave the product like this, that's perfectly fine. I know what you mean. Visually, this maybe makes better sense. But honestly, if I want to draw this the proper way, here we have a carbon, a carbon, a carbon, carbon, carbon. So 1, 2, 3, 4, 5. All right, so 1, 2, 3, 4, 5. The ring opens up into a straight chain. And then it looks like on group number 1, I have the OH group. And on group number 5, the other end, I have an iodine. So if you want to redraw it, maybe a little bit better, more representative of what it's supposed to be, you can do this step. However, if you leave it with that ring and that bond erased, folks, I know what you mean. Again, I'm not that picky when it concerns the test and stuff. I'm going to give you credit for that. So you at least know what's going on in the reactions, and sometimes it's all that matters. All right, let's take a look at C. I have this benzene ring. This benzene is an alternating double, single, double, so I'm just going to draw a circle there. They did not do that in the problem, but I'm going to do it at shorthand. And then here it comes out. Then it goes back down to the O, which means there's a carbon here. And then that oxygen is directly attached to another ring that has an alternating double, single, double. All right, so here's the structure. I'm going to react this with HI. I'm not going to redraw it this time, but we know that that oxygen is going to get protonated, and that oxygen is going to make a decision. Where do I break? All right, well, let's look at the choices. If it breaks to the left, up here, kind of toward the top, then this carbon is a benzylic carbocation. That is very stable. That's more stable than tertiary sometimes, because this benzylic carbocation, folks, is delocalized, and this delocalization can now leave the ring and venture off toward that positive carbon that's directly outside of it. So delocalization improves the stability. Now, we can have tertiaries and tertiary benzylics and stuff maybe too, who knows? But this is at least a benzylic carbocation. Over here on the right-hand side, this oxygen, if it cleaves here, well, this is directly on that ring. And directly on that ring, this carbocation is going to be an aryl. That aryl is very, very unstable. The reason is because that positive charge is on a carbon, and that carbon is also taking part in delocalization, and that positive carbon disrupts the delocalization network that's inside of that ring. Again, that's chemistry 251 topics there. So out of these two choices, there is a difference in the carbocations and the stability. And this oxygen feels much better if it can break that bond right there and take the hydrogen and go off with that molecule. Now, we leave behind a more stable carbocation in terms of benzylic, and that benzylic carbocation is going to take the halogen, and then that halogen is going to be attached to that carbon, and this is going to be the I from the hydroiodic acid that we used. So I don't want to just draw an I right there, right? This is a carbon, and there's something attached to that carbon, and that is an iodine. So there we go. If we wanted to draw this maybe a little bit better way, we can draw this ring structure, and then I can come out and draw a CH2, and then off of that carbon, I also have an iodine. So there's my third bond, and my fourth bond goes onto the ring. So there's the two products for the reaction. Here is the alcohol group, and then up here is the halogenated group. All right, so maybe not so bad. Maybe these are a little bit easier than what you thought they were. All right, so in the next one, I'll have an oxygen, and then it looks like they've drawn it kind of up. So there's a carbon, and then over, and that gets connected to another benzene ring. And then down on the other side of the oxygen, it looks like they went over, there's a carbon, and then down, there's a carbon, and then over, and there's a carbon. Once again, oxygen makes a decision. So if this is going to cleave in half because we are adding HI to this molecule with maybe some heat, then this oxygen is going to make a decision to leave behind the most stable carbocation if there's a difference. So up here, again, we have a benzylic carbocation that can be formed because that carbon is attached directly to a benzene ring, benzylic. And then over here on this side, if the carbon cleaves that bond, this carbon is really a primary carbon. So out of the two, there is a difference. That benzylic carbocation is way stable than the primary. So because of that, this oxygen's going to get rid of that bond, and it's going to take the H with it, and away it goes. There's the alcohol formation. Now, what's left? Well, that carbon needs something attached to it, and that's going to get the I. So once again, if you wanted to draw that CH2, just so you don't make that mistake of connecting the I there, or just changing that to an I, because that's different. Make sure that you represent that carbon, because that carbon is there. So there's the two products that I have from that reaction. Next one, I have a ring, but this time it's not a benzene. It's just a ring. And then off of this, I have an O and a CH2 group. All right, so here's this ring with the OCH2. I look at this oxygen, and if I add HI to it or HBr, it doesn't matter. One of those acids will work. It does the same thing. That oxygen's going to figure out which one to break. If I look at the left-hand side, this carbon is a secondary. If I look at the right-hand side, this carbon is a primary. So it's going to make the decision to right there, and that hydrogen will attach to the O, and away it goes. All right, on top of, and that should be a CH3, not a CH2. All right, so on this ring, what we're left with is a bond that's open, it's available, and the I, of course, goes on to that spot when that oxygen cleaves. So there's the halogen, and then there's the alcohol. Finally, in F, what we have here is a 5-membered ring. There it is. And this is a CH3 and a CH3. So if I add HI to that molecule, again, that ether is going to get protonated. Which side will it cleave? Well, if I look to the left, this carbon that it's attached to, well, there's only one other carbon that it has. So think of this as a primary. And then on this side, here's a carbon, and that carbon's attached to 1 up here, and 2 right there, and 3 down below. So this is a tertiary carbon. It feels really good about the stability of that tertiary carbon. So when this oxygen decides to cleave the bond, there we go, and that oxygen becomes protonated. All right, so there's the H that comes from the acid addition, and then this spot is still opened up for something else. So what is that fourth bond? Well, that fourth bond is going to be the halogen. And here we used HI, so the iodine is going to go there. Now you can leave it this way, or you can draw this a much better way. Let's figure out how to do that. Here is 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbons in total, longest chain. All right, so here's 1, 2, 3, 4, and 5. On the first carbon, I have an OH group, so I'll just draw this down like this. That's okay. And then there's my first, there's my second, there's my third, and there's my fourth. So on the 4th carbon of the chain, I have this methyl group that did not get included. So here is a methyl group. I'll just draw that with a stick. It's understood to be a CH3 out here. And then the other bond, which makes the 4th, is the iodine. So I'll draw another line, and I'll just draw the I represented there. All right, so there is the cleaned up version of the molecule. Again, the ring was formed. That ring is okay. the oxygen will break the ring, and now we have somewhat of a straight chain molecule that comes from this reaction. Now, I do want to do something. I want to go back, and I want to look at E. So I'm going to do something to E to make you a little, I hope not confused, but to make you think a little bit. What if we had a double bond that was right here? How would this change? Would it change the product at all, right? I mean, here we have a ring. We already did this example. We knew that oxygen was going to cleave to the left-hand side. That left me with basically this carbocation that was a secondary on the ring, and that's where the halogen went. Well, if I just draw the double bond right there, if this oxygen makes the decision on what to cleave, over here to the right-hand side, this right-hand side is a primary. That's not changed. Over here to the left-hand side, if it cleaves here, that is a carbocation that's on a carbon that has a double bond. Folks, this would be a Benzylic. And Benzylics and primaries, pretty nasty. They're not stable. This is that whole grouping of the unstable carbocations when they form. So this is not decided by carbocation stability like all the others were. There was a clear-cut decision on which carbon was more preferred because those carbons were way different in all of those other examples. Here, though, we get this primary and this Benzylic, and neither one wants a full-blown carbocation. They just don't like them. And this is where that Sn2 mechanism comes into play. Neither one of these carbons want to go away. The oxygen does not feel comfortable getting rid of one of these relationships because both of them are unstable and crazy. No matter which one oxygen breaks up with, the other one coming for it. I mean, peeping through the windows, breaking down the doors, stalking them in the grocery store, you name it, oxygen is going to be in trouble. So these primaries and these Benzylics and these aryls, all of these are going to be very problematic. Methyls. So we do get a slight different product that forms here in this version. How? What do we get? Well, this is the whole concept that we talked about if there was a tie, or they were so unstable like these are. The halogen that I add to this mix will come in and attach to the least sterically hindered piece. And this ring has a lot of buddies. This ring has a lot of friends that are hanging out in a little party. And this is sterically hindered. The iodine cannot come in and attach to that group or that person that oxygen's in a relationship with because of all of these other things around it that's paying attention. But this poor little carbon right here, that poor little carbon, it's got no friends. No one there other than oxygen. So when oxygen calls the iodine up and say, psst, hey, come and help me out. Both of these things are kind of cray-cray. You need to kind of distract one of them, make the moves on one of them, so that way I can break up with that one and all of the attention can be on you and not me. So iodine comes in and the oxygen is going to cleave here for that reason. That's how these are different. So this is a way that ethers can be tricky for you if you're not careful. When you have clear-cut decisions like we've had in every other example, those are kind of easy. You go with the flow. But then when you get these primaries and Benzylics and stuff that are so unstable, oxygen doesn't want to get rid of any of them. This is where the problem's at. So iodine comes in and it attaches to the smallest piece. That's backward than what we did the first time through. Because I changed the molecule up on you a little bit, just with the double bond. Look at what happened here. Now I have this other piece, and this other piece is a ring with a double bond, and there's an oxygen there, and that decided to have the hydrogen. So off goes that alcohol, And here I have the halogen. Now, if you leave it this way, this is a wrong answer. Why? Well, here I have an OH on a carbon that's involved in a double bond. Chemistry 251 called this a functional group, and this functional group was a ene because of the double bond, ENE, and an ol because of the alcohol group OL. This is called an enol. This enol will tautomerize. This is one of those rules that we learned back in the day. And what happens is that the double bond shifts up because oxygen's real greedy. It sees those electrons that carbon has. It's extra money. So oxygen says, give it to me. And that carbon says, okay. And that hydrogen will leave off of that oxygen and go back to this carbon that lost the double bond. So the hydrogen from the alcohol group goes right there. And that satisfies that carbon's need, makes it happy again. So it's not charged. And this ends up with a ketone functional group. And this was a enol ketone tautomer. So this was a chemistry 251 topic that should have been presented. So here, just with the addition of a double bond in the ring, it changes the whole reaction. The oxygen now has a really hard choice between two very unstable Benzylic and primary carbons. It doesn't want to break up with any one of those in the beginning unless it has some backup. The backup comes in. The iodine is able to go on to the smallest piece because the iodine's really big and fat. It can't really work itself into the crowd, but it can work itself in to the single carbon. So off goes that halogen piece. We're left over with the alcohol. Just because this was Benzylic and there was a double bond and an OH group on the same carbon, this allowed me to go back and review tautomerization. So the enol will quickly reform to the ketone, and that is a more stable version of that. However, keep in mind, this is at equilibrium. It does go back and forth, but the enol goes to the ketone a little bit more because that ketone is a little bit more stable. All right, folks, so that's it of the ethers. Can you believe that? So we did like 20 videos, it seems like, on the alcohols, but yet the ethers get a mere 3 videos, and that's about it, because the good news is that these reactions, there's very few of them. So we like that when that happens, right? It's only HBr and HI. We don't have to worry about any other reagents. And the question here with ethers is just really, where does the oxygen break? Where do they break? And that's the question and the answers of how you determine these types of reactions that the textbook will throw at you. All right, so in the next video, what we'll do is we'll go on to our next section. So we're done with alcohols, we're done with ethers, and now we're making it to the epoxide section. So what is an epoxide? How do epoxides react? I hope they're very similar to alcohols and ethers, and they should be because they're grouping them into the same chapter. And we'll see what goes on with the epoxide functional group.